So this is our first open version of this. This is we originally started this as an internal thing to sort of, learn about new technology and stuff like that. But it's kind of turned into some other, gone into some really unique, fun directions. And we decided to open this up to the to everyone. And really, our intent with this is, solving problems with open source, tools and certainly integrations with our tools. So we get into things like, here at Atomic, we deal with OSEC, which we run, which is a host-based IDS. We also deal with work heavily on tools like mod security, which is a web application firewall for Apache Nginx and IIS. We do malware countermeasures, which this is kind of in the theme of malware countermeasures today. We also deal with things like GR security and OpenVez, or Greenbone, what it's called now. It's a vulnerability scanner. But basically, it's all the universe of security tools and technology and whatnot, and really just kind of, it's all very hands-on. So today, what we're working on is we've captured malware. One of the guys on here today, one of our panelists today, is Jared, who had captured some malware that he found on a particular environment. And it's both PHP and binary malware, and we've taken apart the PHP and some previous ones. Today we're going to be doing the binary malware, and which I've been doing malware research since the 90s, and I've used a lot of different tools. This is the first time I've ever used this tool we're using today, which is called Ghidra. It was developed by the National Security Agency, was released, I think, I don't know, not that long ago, probably only a few years ago. I personally have been using tools called lately. What I mostly use in the last few years, one called IDA Pro, which is a decompiler or disassembler that lets us take apart binary malware. And I know it really well. And I've used other tools, and I'm going to show a couple of them, a couple of the ones that you're going to have access to. But Ghidra is really the main one we're going to be focusing on. On the screen here, you see Tater Tot. He is the younger of the two Samoyeds I own, and he is currently behaving very well. So hopefully I won't be interrupted very much on this front. Just for a moment, I needed to notify a few people that were started, that had asked me to notify them. I promise I won't be doing this in the future. I'll try to stay on track. This is going to be recorded. So for anybody who was not able to join us today, we did this for you. So just some backstory on how I do malware research and what our environment looks like here. I always do malware research on a dedicated system. We got really into the weeds on the setup of that last time, and if anybody's interested in that, please let us know in Slack about this. And I should probably pick one. I'll be using the Atomic Corp channel on the Atomic Corp support Slack. If anybody wants to ask questions there, you can ask questions in here. But back to our environment. So I have a dedicated virtual machine server in my network here. I put my malware research systems on a private network off of that, and then I get into it by way of, in this case, I remote in by way of screen sharing, right? So this is called Spice. One I'm using, you could use RDP or whatever, but the intent is that if you're going to be doing this doing malware research, malware itself can affect your environment, right? And so you want to compartmentalize that environment as to the best of your ability. Mine is a dedicated virtual machine, which I only use, I create one each time I do a separate piece of malware, and then it lives in a network where I have created, I've either compartmentalized it completely where it can't get to the internet, or in this case, it's running through a transparent proxy server. So the virtual machine has no awareness of that proxy server. I've done some things with SSL so I can intercept all that stuff which I could always go into at a later date. But suffice to say, I have very strict controls over this environment because, you know, if I wanted to run it and I wanted to take it apart, I could do that. There's no need for me to do that, I hope, today. I'll mainly be doing that by way of Ghidra. And yes, this is Fedora. You're looking at a Fedora desktop. You could use any tool you want, or any desktop you want. The Ghidra project is linked in the Slack channel, and I'm going to fire that up. Well, let me go over what I've got first before we dive into that particular step. So let's start with the malware. This was captured off of a compromised, and if I'm wrong on any of this data here, Jared, let me know. Off of a compromised Linux system. It happened to be a not up to date thing. Was it CentOS 6? I think.
Yeah, it was on a CentOS 6 box.
Yeah, CentOS 6 box. It happened to be acting as a web server. And the malware, it came in many variants, right? So there's PHP malware in here. We're going to be looking at the binary malware specifically because we did the PHP one already. So first thing I always do here when I'm starting on this is there are a couple of command line utilities in Linux you can use to just kind of get a feel for what it is. This happened to literally be called, I think, Linux x86. So that's kind of an obvious file name. That's not going to be normal, right? You're normally going to have something really bizarre in here. And because I was playing around with this before, I'm making a copy of it there. All right. So the first thing I use is a command called file. Now, bear in mind, the forensics tools I'm using can be attacked by the malware by virtue of me analyzing it. This has absolutely happened. This is why you use a dedicated system that you then rebuild each time. The tools file, the tool strings, basically all the things I'm using here, there have been attacks on the way these tools get used to compromise the malware research environment, or even detect it and hide. I'm going to skip over that stuff. We could certainly, if there are questions about that later on and we want to get into it another day, we can do that. But let's start with what these are. So the file command is reading what's called the magic header off of the top of a file, right? And that can tell you a lot about the file without running it. This is telling me that this is a 32-bit binary, which is interesting on itself. And it's an ELF. That's forget off the top of my head what it stands for, but that's a standard Linux binary. And it's built for an Intel CPU. So aside from that, the data that really interests me here is that it's statically linked, which means that it is not using any external libraries. It's all self-contained, and that means that you're going to typically see that with malware. If you see it's got something that's dynamically linked, an example of that would be, let's look at Bash or something. You'll see that it's dynamically linked, right? And you can tell what a binary is dynamically linked at with the next command I'm going to use here called LDD. So if I look at Bash, these are the parts that it's pulling in, right, in Bash. Now, if I look at this malware here, it's static. It won't have anything, right? It's not dynamic. That's important because you can use that as a way to determine if the malware, I mean, typically speaking, if something is statically linked like that, I mean, it's sus, right? Like, but it's not unacceptable. Lots of languages will do static binaries, but it's the intent here is that it's bringing all of its parts along with it, and it's not relying on the operating system. This is the other one I use, and this is just a quick way to strip all of the ASCII strings out of a binary. Again, I'll do it on a legit one first, right? Oh, if I can spell strings right. Right, and it tells me things that if there's an ASCII human readable string in the binary, it's going to pull it out for me, right? So I use this as a quick and dirty way to look for really, really, really basic stuff before I get into the hardcore tools. Like I would do strings and I would look for URLs, right? So I did strings on this and I grabbed for HTTPS. I probably won't get anything. Right, there you go. You might get lucky, right? If you're looking at malware, it might give you a URL to a domain. If the malware itself is nothing more than a simple loader, it might give you some information about it before, without you having to get into hardcore analysis. So let's do strings on this binary and see what we get. Super useful to know right here. We'll go into what this means here in a second, but I didn't notice that until just now. That's super handy to know. So if I'm poking around through the strings in this, I'm looking at this code and I'm not really seeing anything pop up. I actually know why, but I'm going to go over some of the reasons why you might not have anything in here. So malware might be what's called crypted, and actually, coming into this, I thought maybe this was what we call crypted malware, where basically you have a tiny piece of binary code that lives at the top of the malware, or the beginning of when it runs, and then basically an encrypted section after it. So you have this loader that in essence loads another binary behind the scenes that happens to be encrypted, and that's done. Crypted malware is done to get around signature-based like AV and things like that, right? Like each time it runs, it recrypts itself. So each time it runs, the whole binary is totally different looking hash-wise than it did before. Now, I just happen to know that this one is not that because it's using this UPX stuff. But before I go into that, because this as a bad guy, I would want to hide this. I'm going to fast forward to what this is. This is a compression system. This is basically a way of compressing an executable file to make it smaller, right? And they made a mistake. They let us know that. So we're gonna fire up Ghidra first and look at this before we decompress it, because it's a perfectly valid binary. And in advance, this is honestly the first time last week was I installed Ghidra. I ran it for like 15 minutes before this call, so I'm gonna say right off the bat here, I'm going cold into this tool. I did a little bit, poked around it just like for a few minutes, but I am not an expert in this particular tool. I know IDA Pro and GDB and tools like that really well, but this is my first time going through this environment. I do know this much. Got to start a new project. And Ghidra, we could probably go into this at a different date, does allow you to share the analysis with another person or people or group. So they call this research. Let's call it research malware x86. So step one, you create yourself a group, and step two is to import a file or files into this. And I'm going to pick this x86 one that I just copied over. I like to work off of copies of the original because all of these tools can modify the binaries, right? And so you want to work off of a copy, that way you don't trash something in advance. So let's load that guy up, and it's going to pull out a little bit of information. Basically, what we were looking at before with the file command. So it's telling us it's a x86 CPU binary, and telling us what the magic header is here in this case, the LE header, right? The ELF header. All right, so let's start with some info it gets off the bat that makes me I know why it's saying this now, but if I were to see this in the future, I would right away know that my job is going to be really hard. So it's giving me a little bit of info about it, saying I found one function and one symbol and 9 data types. Okay, that's really bad when you only get that much. If I were to see that in IDA Pro and I didn't know this, didn't know what I was going into, I would basically say this is encrypted malware and I'm going to have a really hard time with this. But let's keep going on that. Now, the reason why it's only showing me this much stuff is because it's not encrypted, it's compressed. And what we're seeing is the function to decompress it. So we've got this binary here. I'm guessing I have to open up something. Default tool, might in it. Oh, yeah, there we go. Okay. So that was me. I had opened up that before, but when it first starts up, it's going to ask you if you want to analyze the malware. When we're looking through this, you have a whole bunch of utilities in here, and you mostly can just stick with the basics. You don't have to go and modify anything in this. I am going to turn on this decompiler parameter ID. This is something that I'm used to in IDA Pro. This is more for me than for you. If you like the way that this lays stuff out, go ahead and use it. It won't hurt you if you don't. But its job is to help me try to variabilize things better. And we'll kick off the analysis. It has a whole bunch of plugins from what I've looked in the back end here that are doing things like stripping out the strings like I just did before. Did it really finish that fast? That's way too fast. Seems like it should have taken longer than that, especially given how short this is here. We'll reanalyze this sucker. All right, we'll keep going. So, okay, so in the first thing I would want to look for anytime I'm dealing with malware is if you're a programmer, you would know that usually we call where we start main, right? And this is a navigator of what we found in here. So we've got some functions, 3 of them, right? And the entry point right there, which is not great. If this was encrypted malware, I'd be concerned, but I can actually look here at the top, and I've seen enough of this garbage over the years to be able to say, okay, this is actually compressed, not anything else. But what this has done is it's picked out the functions and has tried to render those functions into a human readable format, decompiling it. I can tell this is a compression algorithm because I'm cheating at this point. I already know that it's compressed. So let's go and do this again. This time, instead of, and we're going to decompress the malware and we're going to load it back up and see what it looks like compared to this. We had 3 functions this picked out in here of the raw stream. Probably don't need to do this, but so the tool I'm using here, we know it's UPX, right? So UPX is one of them. You can do UPX minus D, x86, and boom. There's our decompressed binary. So it's 7 megs. That's not unusual, something that's static. And I'm going to repeat this on here, and let's see what we got this time. Oh, okay. All right, so this is Go. This binary is, this binary is written in Go, which makes the static so much easier. So what's interesting is that it's 32-bit though. You had to work hard to do that. But aside from that, we've got a Go binary, which can have this. Let's try. Do I have Go on here? Version. No. They mask that enough. So let's take a look at this. So structurally, C and C++ and things like that, those languages, they use a main, right? That they call the main, the function call main. Go doesn't call it that. They call it main.main. So what we need to find well, first let's just strings it and see what we get in here. If they obfuscated it, it'll be a mess. If they didn't obfuscate it, it'll tell us all kinds of great stuff, like exactly what is linked in here. And this is still the header. I'm going through 7 megs of text. Ooh, I saw a TCP in there. That's a good sign. If this isn't encrypted, it'll get really good fast, like probably towards the end. Oh, yes, awesome. Okay, so this is definitely not encrypted malware. We can start to see these could be the names of functions. These could be Yeah, I mean, these could be like raw SQL and things like that. That's actually a really good sign. If we start to see stuff like this when we're taking apart the malware, we know that we've got good data to work with. Yeah, it's like SQL stuff in here. I saw the word password. Cookies, yeah, it's gonna look, probably got some kind of web library in it. Yep, there's our probably function libraries. Let's just dump it all at once because this is what I was expecting to see. Now we should actually even get the, let's just do it fast. I will bet you we even get stuff like, yeah, here we go. These are the libraries they use. You can tell where they compiled it, right? They did it from the source star like that. And I'll bet you if we went and started looking out on, if we started looking out on GitHub or something like that, we might even find these libraries source code, which is super useful for breaking these things down because it just looks to me like they're just using common libraries. All right, so that's all well and good, but I will bet you Ghidra will do this too. I mean, obviously for me, I'm just used to doing searches in this format pretty quickly. So will it reanalyze this or will I have to rerun it? I think it's going to reanalyze it. I don't know if I need to do apply and then analyze or just do analyze. Did you do anything? I think this is still looking at the older one. So let's, no, we don't want to do that. All right, let's just do a new project because I'm not as familiar enough with this tool to know if I'm doing this the right way. Let's call it test 2. Don't save this. Hopefully it's not cached. That's better. That's better. We've created the project. Some usability there. I'm not, excellent. This is good. This is very good. The compiler reference. There we go. That's what I'm expecting. Normally, yeah, I'm used to whenever you're running this through like a IDA Pro, it's not fast. It's 7 megs is a lot of stuff for it to go and analyze. So it's crunching through a bunch here. And I'll bet you we'll start to see this. Yeah. This is where it's gonna get super messy. And in the background, I'm copying over some tools, some other tools that I use with IDA on here to break this down. But functionally, sort of like kind of to set the level set where we're going with this. The idea is that one, we want to understand what the malware does, right? Because malware might be a loader, and it might be loading malware from something else, and we since we're trying to come up with countermeasures is our intent of this exercise is to obviously understand it, but we want to come up with a countermeasure for the malware. So it helps to look through and see what it does, right? Because it might say, hey, there's this other include, like we know from what Jared collected, we had a bunch of other code around this thing, and I don't know if it installed that stuff or that installed this. Like I'm not sure what the chain of events was there. We didn't really get the info. Oh, so look at this. It's still going on. I'm gonna break down what the challenge is here with this. But ultimately we want to take it apart, obviously, because it's super fun and cool to understand how it works. But then also we want to try to see if there is anything in this that will lead us to something else that we might also care about identifying. So let me just kind of go over the windows that we're looking at here. So this window here is basically looking at the we've got a hex breakdown in here of what the code is and what it's doing. But this is assembler. Okay, this is machine code, and it's literally the way that the OS interprets it. If you've used a tool like IDA Pro before, this is really our world. We're up in here, and we use things like a graph, which I think is probably in here on the left, try to understand the code. The people I talked to, they've used Ghidra, have told me that they don't even know assembler, which is a good sign, because understanding assembler is it's a huge challenge. This is not like a programming language that you would look at and just be able to understand that this is an if-then without understanding how a machine and a compiler compiles the code of an if-then into an if-then, right? It'll look like that, right? The cool thing is this is actually decompiling it over here. And so that's an example, right? I mean, we can find a function in here, and we can actually run it, or not run it, but we can actually render it into a human readable format. Now in C and C++, this is really, I have never done that with Rust, but I've done this with Go before. And if I hadn't run file on this and I'd loaded this up, I'd immediately know I'm looking at Go. C and C++ will have, assuming somebody hasn't obfuscated the binary, they haven't stripped, even if they strip the symbols out of the binary and things like that, that would help us with debugging it, we would basically have a handful of functions. Go is not like that. So this is our list of functions, and you see because it's Go, I have to see if we can find the original names of the functions. But for the sake of what I'm looking at right now, Ghidra does not know what the functions are named. In essence, I do not know from this list where main is, where the start of the program is. All I have is this massive, what's going to be, I know, a massive tree of functions. So I have a function group called 08, and inside of 08, I've got 3 more function groups. This is grouping the functions together. I get what it's doing. And I'm going to bet you I'm going to keep going down this, and it's just going to keep getting bigger and bigger and bigger. And I wish it could tell me how many functions we're looking at in here. You look at this, right? This is, I don't think that, practically speaking, you would ever have a chance in hell, or in any reasonable amount of time to, I mean, how many are in? It's probably 1,000 functions to find. You would have to find main, and each time you find the function, you'll see this. It references another function. This could be something stupid like, I don't know, chmod, right? A chmod function in there. But if this is anything like IDA, we might be able to find it. We might be able to recreate a function table out of this mess. Like, so basically I have all the code, I just don't know what any of the function calls are named. They're all named something random. Like, I have something that assigns to uvar2 by running this function that does something that I do not know what it does in here. Okay, so how do we find that? Let's try and search our strings for, how do you tell it to do, I guess, all blocks? What do I tell it I'm searching for?
That's a good question.
Okay, maybe main.main. No.
I know Frank is more familiar with the Ghidra.
All right, let's try that again. So I'm going to search for strings. Well, maybe there's like a search for a specific thing. Maybe it's like search program text for, there we go. Here we go. So Go calls main.main, or at least main.main when you're looking at it in a decompiler. That's what we're looking for. If I was looking this in C, I would just look for main, but I want to look for main.main. If I look for main, I'll actually find I'll find a lot of stuff that I don't want. No. Wait, all blocks. No. Oh, this will be hard if I can't find that. Ah, wait, hang on a second. So, okay, so Go has this, and I know I'm going way down into the super expert layer here, but it has this, basically this PC IN tab thing, right? And that's basically, this is where you look in this is where I would look in IDA to find main.main. And does it, can I just search in this block here? This, or I have to use this search tool? Program text. Let's try that again. Let's try main.main, all fields. Well, before, since I know my I know this better. If I do strings on x86, main.main, are you in here? Yes. So it's in there. All blocks. Search all. I would actually put the search here. I'd be like, let's try that again. Search for strings. All blocks. Maybe I do it in here. I'm not sure. It's not pulling up any strings though when I do that. No, maybe it's got an ASCII search. Search. Ooh, memory. All blocks.
I would think it would be search for strings,
Yeah.
but that's not happening.
So I'll bet if I keep scrolling through here though, I'll find it. Ooh, oh, let me get there. Yeah, see, it's going to be here. It's going to be in this. So I know it's going to be in this, which is not helpful for anybody who's didn't know that going in here. Ooh, wait, no, that won't help me. I bet you I won't get it made. No, I won't get it in there. As I go through a megabyte of trash. I could have just blasted right by it. This is really good sign though, because if you see this stuff, these are actually the names. This is we can use. I know we can reassemble this and get the main function out of here. Man, come on, give me a search that works. Address table, scalars, strings, program text. Maybe I have to select the area I'm in. Oh, that's good. That's different. Maybe that's what I have to do. I have to tag that section. Yes. Awesome. We got it. Okay. So this is telling me in memory where main starts. And since I know that, I'm gonna write this down. I'm modifying my script behind the scenes here. So okay, this is a pointer. With that pointer, it points to a list. That list is the name of all the functions. So by running some code that I'm copying over here, and I'm copying this hex value into it, I should have a, all right, run a script. How do I run a script? You would think this is it, but I played around with this earlier, and I think this just gives me the output of the scripts. So obviously you can run a script. And what I'm going to do is I'm going to run this. I'm going to run a script that reads that, and then I mean I could do this on the command line too, but it reads this address here, and it's going to output it back into. Here we go. I just had some people ask how long we're going to run. I don't know until I make some progress, I think. Probably until at least 2. Window, Python, script manager functions. No, that doesn't help me. Script manager, what is this? Ah, okay. All right, let me go and see my code. Just copied. All right, here's my Python, right? And so this guy's job, what he does is he reads that magic go PCLNT tab, right? That thing that we were just looking at in here. And what it's going to do is it's going to crawl through all of these functions, all these, well, I should probably help, it'll help if I show you, but it's going to crawl through those fun, whatever rando names. And it's going to try, and I hope this works, it's going to try to reassemble the function. Now, how do I add one? I have to do like, there's a new, what's in function ID? This is a function ID. So can I just add? No. Really?
There's a plus sign up there at the top. I'm not sure.
I didn't see that.
There you go.
No. Thank you for not adding. How do you get it into add mode? Edit. Nope. Tool option? No, not that. Yes, I could read the docs. Thank you for that suggestion, everybody. Do you want to watch me read the docs online?
Not particularly. It's much more fun to watch you struggle.
Oh yeah. Oh. Okay, wait.
Oh, that works.
Hang on. I think I got it. New. This is good thing this is in Python already. So I guess the only options are Python and Java. I've used one. Is there a way to add? Okay. So can I upload? Select the font. Save as. Refresh the contents of the editor from the file on the disk. Well, how do I load the file on the disk? Maybe I have to put it in the directory. Let's try that. Okay, we're gonna copy func to Ghidra scripts test. What did I call it? Test1.py. And then, Bing pot. It worked.
Total Bing pot.
But do I need to set the Python code for this? Run script. Let's see what happens. That is a very good sign. This is exactly what I would expect it to do. Okay, so if I go back into this, functions. Yes. Yes. Aha, look down here. Oh, that's really good. Look at this, the names. I'm seeing database. I'm seeing, if you couldn't see that, I saw one that would look to me like a package, like SSH listener.
Mm-hmm.
I think I just saw one that said Slack.
Oh, wow.
Okay, so in our symbol tree, we have a function that is populated. Look at this. Okay, how do I make this bigger? I don't know. Make this bigger. Okay, I'm gonna apologize to everybody in advance that this thing looks like we're reading an eye chart. I'll just try to list what we're seeing in here. Auto run dropper. Oh my God. Ah, well, this is a little better. And can I make that bigger? No. It's so annoying. Okay, here we go. Here we go. That's great. Look at this. It actually captured it down here too. Oh, we'll use this guy to view through it. Okay, so we have a function called anyway, don't know what that is. We'll look at it in a sec. We've got auto run dropper. I'm going to say probably downloading stuff. We've got an SQL one it couldn't figure it out. OS functions, these are probably things like chmod and shown and rm and this guy, StealthWorker. I know what StealthWorker is. We'll talk about StealthWorker here in a second. And there we go. So we got the top level list of the functions. And if I filter this guy on main, hopefully we'll get to main. Yes. We want to do main.main, right? This is where the program starts, right here, main.main. Are we at main.main? Yeah, we are. So this is main.main right here. So I'm going to move this symbol tree back. Please move back. Okay, cool. Can I pull this off? No. Yes. Yes. Okay. So here's where the program starts. Now, bear in mind when we're looking at this as a decompiler, it's not going to know the original. Most of the time, it's not going to know the original variable name. So it's just going to generate these at this level. Plus, we are looking at Go that has effectively been it's post-compiler, right? So it's not going to look like Go. It's not going to look like the Go you're used to. It's going to be C, basically. Basically, huh, a pun. But in here, we can see what the program does. So starting at top, I have no idea. Maybe a locking thing. Getting the time. Getting a random seed. Probably used for crypto. Interesting that it's.
Those are popular right now.
We're going to look at the library. We're going to look at the function calls here in a second, but I just kind of want to peruse through what this guy's doing. This is nice, right? Like sometimes you'll get lucky and the variable name that it's used in here will reference where it came from. And you can get some interesting, that's neat. When I double clicked it went into what this function does. That's nice in an IDE context. How do I get back though? Oh, went too far. There we go. Okay, this is cool. So we've got a really good breakdown of we have a good decompile of this. Now, here's some things you can do with this when you have the code at this level. I can run it again, except I can change it. So because I've decompiled it, I can recompile it my own way. So if we wanted to get into the much more advanced way that we can work with stuff like this, we could actually take the code and modify it. So let's say we're dealing with a botnet command and control system, and we want to get into the botnet. We could actually modify this client, right? We could in essence, we can hijack their code using this and get into it. You can also use this to bypass crypto keys, right? So let's say that this thing requires a particular crypto key to get to a certain part of the code. We can actually bypass it. We could do things to expose it. We can expose the seeds and the values and things like that, and actually be able to take apart the crypto because we're inside the client, right? They can't hide that from us. As long as we can execute the code, we can actually get inside of the SSL or SSH or whatever session. That's for another time here. This is terrific. This is one of the things I absolutely love about working with Go in general, not just in reverse engineering malware, is that typically when you're dealing with pure like C malware, it'll say a function, right? You don't know where that function came from. You're hoping it comes from the glibc that's on your system, but in reality, no, it's not, because that glibc is different depending on the operating system. The glibc used in Alpine Linux version A is going to be different from the version of glibc used in Alpine Linux version B. And that can matter when we get into what a function, what a library can do. What's nice about Go is that it tells me exactly whose version of a function call they're using. Like you know, as an example, right now, I'm working with a Go function that tails a file. Okay, there are multiple implementations of that. I know exactly whose implementation they used, so I could go in there and see what this is. This tells me right away this thing runs as a daemon. Sweet. I mean, I'm not surprised by that. This is a daemon that's going to run on the bad guys, or that the bad guys put on the system. It's calling that auto run dropper function. A dropper is used to include code from another system, right? Like this thing clearly can reach out to another system and get more code from it. My guess is maybe where might be where some of those PHP ones came from. I'm not sure. We'd have to go. Frankly, we'd have to run it. I'm not going to do that today, but we'd have to run it. Okay, lots of seed stuff, blah, blah, blah. Yeah, it's running some processes. It looks like it threads. Great thing about Go, threads awesome. All right, let's look at some of the other functions that we've got in here and get into the weeds of what they're doing. This thing is a service that connects. I can tell by looking at that. It's connecting to something, and I'll bet you the dropper will tell me what. And then it waits for commands, and then it has all this huge function library that it can go through for that. So we will take. How do I make this smaller? Let's go back to our function library, which is now gone. No, wait, that's not gone. And let's see what else we've got going on in here. This is terrific. This is so much better than IDA Pro. I am sold. This is awesome.
Good.
All right, let's look at this first function here, because it's named really oddly. Oh, now I understand. So this is probably this might be an internal Go thing now that I look at it. To handle, yeah, this probably is here to handle running, you know, basically the overhead of being able to execute as a 32-bit binary. How do I get to the? Is this changing while I'm doing it? No, we don't need the script manager anymore. Definitely a tool I would use. I would need to be running on multiple monitors. Yeah, here we go. Yeah, this function says go to that function. That's not surprising. Can I put this back in here? I'm gonna put you back. I don't know. We'll use some X11 tricks here. Somehow it doesn't go away. Let's take a look at this guy, or that guy. Let's look at this one. These are probably just nothing more than, oh, how do you make it load? Show me what you're doing. All right, maybe I need to do window code browser. I lose my window, I'm not gonna be able to get it back again. I just don't know enough about navigation. Let me show my code browser. No, I lost my code browser. How do I get it back? Send help. Let's see. Functions, listing.
That's not it at the bottom? No?
No, this was me running my script. This was the
output. Okay.
That script that glued this stuff back together. Make a selection. I mean, it's selecting it in here, but that's not what I want. Oh, wait. Let's try that again. Clear code bytes. No, that's me modifying the code. I'm super happy with the way this works. It's just I got rid of a window and I don't know how to get it back. You think, okay, comments? No. Not that. It's got to be under here, right? Bytes. No.
Nope.
Brute forcing it. Decompiler. Yes.
Okay.
But go back. Connect back into this window so I can see you. All right, let's take a look at this auto dropper one because that looks interesting. Our output of all this, and I noticed a little bit of this beginning in the when I first ran it, is it does hash this stuff, which is useful. But when we get into, yeah, there we go. All right, that's working right. I'll just pin this to the top. When we get into writing our countermeasures for this stuff, we'll look at a couple of different ways of doing that. One of the things we can do is we can actually write a ClamAV signature for this kind of stuff that understands the binary. In essence, it actually understands the assembler. And so we basically we look for things in the binary when it's getting loaded up or getting processed that are a pattern, right? It's what we call a binary signature. We can also do hash-based models, but as I just showed before, this thing is compressed. So potentially each time it runs or potentially each time it gets distributed, that hash is going to be different. So there's no, I mean, you know, doing a hash-based signature is very simple and fast, and it scales great. Writing a binary signature requires this level of analysis where we actually look at the code and understand how the code works. All right, let's break down how this function works because we're getting close to the end of doing this. I'm always interested in whatever seems to be the network calls first because that's where we could find more breadcrumbs in the malware. Auto dropper is a very commonly used term for this technique. I mean, you know, it's easy for me to know what I'm looking for. If they would have called function B, I'd be going crazy trying to find it, but they called it auto run dropper, so that was really useful for me to figure out what I'm looking for. So I'd crawl through here looking for any kind of network call or something that might be assembling a name, right? So a technique that'll be used by malware droppers here is it's going to use a randomly generated domain name, right? Like if you've ever seen these garbage names, it's just random characters and maybe off of a subdomain or even the top level domain itself. That's how this works. This thing has a seed. It gets when it's installed, it uses that seed to generate that random name, right? So it might not be as obvious in here as go to http:/ fill in the blank. It might be go to http: some variable. And that's what this looks like it's doing in here. It's assembling some kind of weird variable right here. It writes that to a file. That might actually be post download. Now that I think about it, this might be it. Yeah. So yeah, this looks to me like this function is creating a file. We've got a couple things in here. Oh, init. Let's look at init instead. Init's where it's going to start. So init's going to run. He's going to say OS init. These are right here in Go. These are basically like includes. So you say it's saying functionally the Go programming language is saying I need the following parts. OS is a top level library, and off the top of my head, I mean Jim, who's in here, who's on as an attendee rather than as a panelist, would know all the things that OS can do off the top of his head, but I know it does things like OS means chmod and chown and remove and things like that. Format in Go is for printing things. Path, file path, this is probably an internal thing that they're using. Strings is also maybe an internal thing. And then IO utilities, maybe writing files and things like that. And let's look at, all right, so this guy runs and he says, go run auto run dropper init, which is what I'm in right now, right? Yeah, this guy. And then blah, blah, blah. And I'll bet you if we looked at main, it did call this what it can do. All right, we're coming up at the top of the hour here, and I certainly want to be sensitive to everybody's time. So I'm just going to do a brief overview now of what kinds of things I can tell by looking at this code that this particular malware can do. It has a dropper, which means it's designed to pull in other executables or other capabilities from a remote system. I don't know where yet. We have crypto functions in here. Pretty straightforward. Probably just used for obviously used for creating an encrypted session at the very least. And this is a generic library. It's nothing related to the code, so they're including it. I'm not even going to bother looking at it. We have a group called C, and in that, lots of things that I'm gonna look in later on. That knock knock one sounds super fun. Usually knock knock is a way of identifying a system through some sequence of events like port connections or something like that. We've got database connectivity capabilities. So this thing is able to understand SQL and talk to databases, and this library is generic enough so it would understand MySQL and Postgres and probably MS SQL and things like that. E doesn't look super interesting. It understands things like hex and JSON. This is probably baked in, probably nothing unique to their code. They just pulled it in because they needed it to understand some different formats. This is for things like basically strings. This one, on the other hand, because it couldn't identify what these functions were, these may be related to their code, or it just may be that my script wasn't smart enough to link those together. I'm going to skip those, and we get into the GitHub stuff. These are tasty. So we know exactly what libraries they're using, and we could probably look these guys up to figure out better than looking at the code over here, right? We could go to this specific GitHub, right, and see the original code to see what it's capable of, rather than trying to reverse engineer what it does from all of this, right? This is interpreted, and I'm gonna, because that's an interesting name. Like inflection could be completely benign. It could mean nothing. It could mean something totally interesting. We'll use this as just a quick example. Oh, and in case anybody wanted to know, this is already identified by malware tools. So if you were to go and feed this malware in here, you'll see a lot of what IDs it already and what doesn't, right? This is not unusual for Linux malware. A lot of these desktop-centric malware tools would never bother with the Linux malware, right? That's not really their wheelhouse. But these guys do track Linux malware. But let's take a look at this site here. Nope. What do you do, inflection? Pluralizes and singularizes English nouns. My guess, maybe this has some kind of
translator
or something. I mean, it may be that the bad guy included this, or it may be that the include that this guy is using includes this, right? So it may be intentional, it may not be intentional. Let's give it another couple minutes just for me to browse through these things real quick, because I'm super interested in what these are. We have FTP capabilities. We've got, I have no idea what this does, but it's easier enough for us to look it up. Not sure. Go Damon. This is turning into this one I know. This is used to make this thing work as a service. That logs. Probably sends its logs to the command and control node. We've got a crypto piece here. We've got a bunch of hash function capabilities. We've got, again, this is probably internal stuff. The logging stuff is delightful. I'm going to go check that out later on. I've got main threads. It's Go. Go is a great great threader. Got some math functions. That's not unusual. Sassel. Okay, that's interesting. That would be used for this can could potentially be used for oh my God, I can't say the word mail. I would expect to see Sassel for something that's got the ability to act as a mail server. Then we've got where did my Sassel one come from? You're over here. Yep, Sassel. MIME reader. Either be probably related to the mail piece, so you could send or understand files. Again, it might just be included in the malware because it was included for other reasons. Great big net library, all the stuff you would expect in a networking library. So this definitely would be fully capable. See these right here, fully capable of crafting raw packets if they wanted. So it could be a DDoS. It could have DDoS capabilities. It certainly has libraries for it. And if we were to go through the main function deeper, we could actually go through and look at what those capabilities are. A lot of raw networking stuff. We could skip those things. It's got the full suite of libraries though, so it could do everything from crafting raw packets to establishing an IPsec connection, right? OS, I don't really need to go through this, but these are all the OS functions it can do, which is literally everything that glibc probably can do. Runtimes, don't care about you guys until I do, but yeah, that's threading stuff. That's just baked in. This one, worth Googling. So StealthWorker is the name of a Golang piece of malware. Obviously, they're using it. It could be that. I didn't notice in the these if StealthWorker comes up. Well, yeah, okay. So these guys catch it as StealthWorker. Yeah, there are, by all means, you can Google StealthWorker malware. It's the code is shared, right? So all the things that it can do are it's extensive. It's definitely targeting control panel environments like cPanel and Plesk, but also generic things like CMS tools. Like it understands all sorts like Drupal, but I'm sure you'll see WordPress in here too. Drupal, WordPress, OpenCart, Worker W. I'm going to guess that means WordPress. No, actually WHM, that's the business automation component of the cPanel platform. But it's definitely got the ability to raw understand all sorts of environments here. Yeah, here you go. There's WordPress right there. Yeah, so StealthWorker is pretty extensive what it can do. I know it can act as a command and control node. It's smart enough to analyze CMSs as well as environments like the hosting platforms like Plesk and cPanel. T, probably nothing interesting in here. Time functions and whatnot. And then we have more networking libraries. Got a very, looks like an extensive HTTP one. Yeah, even HTTP2. But that's probably generic. My guess is these are probably actually referenced from StealthWorker, and that might be the one to go through and start ripping it apart. If I can find where up in my code language window is here. Yeah. All right. At any rate, I don't want to keep going on here to hog everybody's day. But this is going to be this is our regular event on Fridays at 1 Eastern. Our goal with this is to go through the life cycle of malware or attack vectors and come up with countermeasures. And those countermeasures can be in web application firewalls. They could be in file-based IDS, like we can do with CLAM or FA Policy D. It could be related to tools like OSEC, which we're part of. We can get into vulnerability scanners. Given the current thread that we're analyzing malware, we may revisit Ghidra again. Absolutely, if you're interested in Ghidra or something else, let us know in the Atomic Core support Slack. I'm also on the Rocky Linux Mattermost security channel. I'm part of the, my name is Scott, by the way. I'm part of the Rocky Linux project, and I specifically in the security group on the Rocky Linux project. So you can always, bring up topics over there. But I think what we're going to follow this up with, or our intent with this particular series, is we're going to follow this up with countermeasures, right? And we're going to probably start with tools like ClamAV and SSDeep maybe next week. But certainly you can bring them up in the either of those two channels, either the Rocky security channel or the Atomic Corp support channel, and ask us if there's something you want to get into, or for that matter, if you want to present. We're just trying to make this practical and hands-on so people can learn stuff and get exposed to tools that maybe you haven't used before, or ultimately our goal, of course, is to come up with ways to defend against this stuff. But we're always interested in other topics and how you can leverage the tools that we're using on the open source side to overall, solve problems. On that note, everybody, thank you for joining us. I very much appreciate everybody popping in here at the last minute. I know it seems a little chaotic. I kind of like going cold into a tool like this because I think it gives, a legitimate experience of what it's like if you're trying to use a tool like this for the first time and you've never done it before. And you could see that even me, I struggle too. Right. So never, don't let that stuff overwhelm you because you think, it doesn't overwhelm somebody with experience. It absolutely does to me too. So again, thank you again, everybody. Please, if you're not subscribed to our Slack channel, let us know. It's open for all and we're happy to help you guys out. So have a good one, everyone.
Awesome.
Happy Friday.
Thank you, Scott. Bye.